So today we are going to discuss about the Kronig Penney model related to nearly free electron theory. If electrons can go inside the periodic potentials, what happens uh, in crystals that we have already encountered in the last class, where electrons are being treated as the Bloch electrons, and the Bloch theorem has been developed with the periodicity of the lattice. So moving on to the elementary band theory and related the Kronig Penney model we will discuss today. So in a nutshell, in the free electron theory, uh, constant potential was assumed inside the solid, right? And in reality, the presence of the positive ion cores gives rise a varying potential field. And in a simple model, the potential can be assumed if A is the lattice spacing and U or W is the width of the potential. And in the limit when this width tending to zero, we get a delta function type of potential. So the traveling electron wave interacts with the periodic potential for crystalline solids, and as well as the electron wave can be Bragg diffracted, or Bragg's law are valid inside the first Brillouin zone. And first in the separation between the first and the second Brillouin zone are called as the forbidden gap, that already we have talked about in the last class. So further going on to the next slide regarding this, gives the this is the simplistic way how we the origin of the bands inside the periodic lattice. And if electrons travels in vacuum, the normal Schrodinger equation would be in the Dirac notation: H psi is equals to E psi, where this H is the energy eigenvalue, that is the h cut square k square by twice m. K takes the value continuously, that's why our energy is continuous for the free electron kinetic energy Hamiltonian. And this is the real situation when the electrons are being traversed by the periodic potential. If this distance are common, that is the lattice constant, this is the physical scenario of the electron that are traveling. That's why we are assuming that the electrons are not completely free, rather than it is nearly free inside the periodic uh, potential. So we have come across the origin of bands inside the lattice, and using the Schrodinger equation, the EK relationship like this: if K takes the continuous values, then EK relation is like the parabolic kind of energy, and energies are being continuous. So continuous energy band are evolved from the assumption of the free electron. So this is the h psi is equals to E psi, this eigenvector. This gives the plane wave type solution A to the power I k dot r. So if these are being modulated in the electrons in crystals, then this Hamiltonian turns out to be h cut square k square plus Vpp is a function of r, which is the electron Hamiltonian in the periodic lattice. And instead of the continuous plot of the parabola, this is this gives the this kind of behavior, where these are the forbidden gaps where Bragg reflection does not apply it. So this kind of behavior are observed, and discontinuous energy bands are being developed. These regions are called first Brillouin zone, this and these regions are second Brillouin zones, and so on and so forth. So the periodic potential, these are the ion cores, right? So electrons are traveling, the associated Dobroi wavelength are associated. That's why if these periodic potentials are the periodic function of this the lattice constant, or the inter ionic or inter um, atomic spacing. So these are the physical scenario where ion cores are fixed in the space and the electrons are traveling. So electrons fields, that is a when the potential is there, and the potential is periodic in nature. So this is the physical scenario of the electron in crystals. So eigenvectors are no longer simple wave, and rather than this simple wave is modulated by the another function which is called the Bloch function, and energy bands becomes discontinuous and thereby called the band gaps, which are being predominant in semiconductors and insulator materials. So how to solve the electron in 1D crystals, right? So these are the simple model where these are the ion cores, and these parabolic type of behavior are approximated as the potential well like a step function that we have already come across in the quantum mechanical problem, starting from the electron in a box to potential well. This kind of approximation are being used for the periodic potentials in crystalline solids. So these dotted lines are the original crystal potential, but the approximate is the square potential well. These are the atoms, this is the electrons are being traversed in the crystalline solids where the periodicity is the lattice constant. So the solution will be obtained by a periodic potential like this, and this x versus v, there is this separation is a, that is the lattice constant, and v minimum, v max, I would like to consider this by solving the Kronig Penney model in the subsequent slides to come. So these are the basics how to solve this equation, and k is the Bloch wave function, the periodic potential is there. I have already discussed, and this is the typical Bloch theorem I have discussed in the last class. So these are the two major difference between the EK diagram in the free electron model and the nearly free electron model, but these are being modulated by not in terms of the mass of the electron, rather than it is the effective mass, which also I have encountered in the last classes, where these effective masses can be lower, higher, or can be negative also. So this kind of energy gap are appeared in approximating our uh, Schrodinger equation theory. So this is the effective mass, and the dependence of the effective mass over the second derivative of the energy with the wave vector are related by this formula. So coming directly into the Kronig Penney model, which we have already discussed in the title slide. So to start with, we already developed the important theorem by Bloch, where the solutions of the Schrodinger equation with a periodic potential are of the form psi k is equals to ukr e to the power ik dot r, where ukr is a function depending in general on the wave vector k, and which is periodic in xyz with the periodicity of the potential, that is with the period of the lattice. We also see that the wave, plane wave e to the power ik dot r is modulated with the period of the lattice, and these are the Bloch functions, right? Another approximation is that uh, we consider n lattice points on a ring of length na, and suppose the potential is periodic in A, so that Vx is equals to Vx plus uh, some integer times A, and the symmetry of the ring, we look the eigenfunctions such as psi x plus A is equals to some constant times psi x, right? So these are the basic approximations by which Kronig Penney model can be solved. So here we demonstrate some of the characteristic features of the electron propagation in crystals by considering the periodic square well structure as shown in one dimension, and I further say that it is a highly artificial model, but it is a model which can be treated explicitly using only elementary functions. That's why this model is so important in solving the one-dimensional periodic, that is periodic potential problem in band theory of solids. So we have qualitatively discussed the behavior of an electron in an underdefined periodic potential. However, in order to know the exact decay relationship, it is necessary to consider a well defined one-dimensional periodic potential. For the purpose, we shall consider Kronig Penney model, and they suggested a simpler potential in the form of the array of a square well as shown in this figure. So the corresponding Schrodinger equation, this is the region 1 and region 2, are of the form d2 psi dx square plus 8 pi square m by h square e psi is equals to 0 for the region of 0 less than x less than a, or the region 1. This Schrodinger equation is for region 1, and this turns out to be plus alpha square psi, where alpha is approximated as 8 pi square m e by h square. And for region 2, for minus b to 0, this Schrodinger equation looks like this, where this is modulated by E minus V0 times psi for the region minus B less than X less than 0, and which is minus beta square psi is equals to 0. Here is plus alpha square, here is minus beta square. Beta square is again approximated as this ratio 8 pi square m by h square V0 minus E. So since the expected solutions of the above these two Schrodinger equations should have the form of Bloch function, this requires both psi and the first derivative of psi with the space, that is d psi dx, to be continuous throughout the crystal. And therefore, let us suppose that the general solution of these two equations, right, are of the form psi 1 is equals to a to the power I alpha x plus b to the power minus I alpha x, and psi 2 from this equation is simply exponential, not the imaginary part, or c e to the power beta x plus d to the power minus beta x for e less than v0. So moving further on, where A, B, C, and D are the constants in the region 1 and region 2 respectively, their values can be obtained by applying the following boundary conditions, where psi 1 and psi 2 must be continuous at x equals to 0, and the first derivative of psi 1 and psi 2 should follow the same behavior quantum mechanically. These are the boundary conditions. Another boundary conditions are that psi 1 and psi 2 are at x equals to 0 must be equal to at x equals to minus b. So these are two boundary conditions which I have to follow for solving the Schrodinger equations in the region 1 and region 2. So implying these two boundary conditions, for the periodic lattice with Vx plus a is equals to Vx, it is expected that the wave function will also exhibit the same periodicity. Therefore, the expected solutions of the above Schrodinger equation must have the same form as that of the Bloch function. So making that equation, we can write psi kx plus a plus b is equals to psi kx e to the power ik a plus b, and psi kx is equals to psi kx plus a plus b to the power minus ik a plus b. So incorporating this requirement at x equals to minus b and x equals to a, these two equation becomes psi 2 at minus b is equals to psi 1a e to the power minus I k times a plus b. Now applying the boundary conditions in previous equations, we write the modified equations like this: a plus b equals to c plus d, I alpha times a minus b equals to beta times c minus d, c to the power minus beta b is equal plus d to the power beta b is equals to e to the power minus I k plus b times a to the power I alpha a plus b to the power minus I alpha a, and beta c to the power minus beta b plus beta d to the power beta b is equals to I alpha e to the power minus ik plus b times a to the power I alpha a minus b to the power minus I alpha a. So these four equations will have non-vanishing solutions if and only if the determinant of the coefficients of a, b, c, and d vanishes. That is, in These four equations can be solved by solving the determinant like this. So using the coefficient and breaking the determinant, on simplifying the determinant, we obtain cos k alpha k times a plus b equals to beta square minus alpha square divided by 2 alpha beta times sine alpha a sine hyperbolic beta b plus cos alpha a cos hyperbolic beta b. So in order to simplify this equation, Kronig and Penney assumed that the potential energy is zero at lattice sites and equals V0 in between them. So they further assume that as the height, right? Let us take a look on the assumption. So they further assume that potential energy is zero at lattice sites here, okay? The dots, the black dots, uh, and equals V0 in between them. In between them, there is a spike like this. Here 0, here 0, and in between them, there is a spike. Again, there is a spike. They further assume that as the height of the potential barrier V tends to infinity and the width of the barrier B approaches 0, it is such a way that the potential V0B remains constant. V0 times B. V0 the height of the potential barrier and B is the width of the barrier, such that V0B remains finite. This assumption is equivalent to, I would say, what this is equivalent to a Dirac delta function. This assumption is equivalent to a Dirac delta function type potential energies where V0 separated by a distance A, the potential energy being 0 in between the delta function spikes. So under these assumptions, sine hyperbolic beta B tending to beta B and cos hyperbolic beta B tending to 1. So this sine hyperbolic beta b in this approximation when b0b remains finite, beta b and cos hyperbolic beta b tending to 1 as beta tending to 0. Hence, the previous equation is looks like cos ka is equals to beta square minus alpha square divided by twice alpha beta times beta b sine alpha a plus cos alpha a, where beta square minus alpha square is equals to 8 pi square m by h square v0 minus e minus 8 pi square me divided by h square. That is 8 pi square m by h square. After being common, this is v0 minus 2e. So since my v0 is far greater than the energy of the electrons, then beta square minus alpha square is equals to 8 pi square m by h square times v0. So substituting this in the previous equation here, this gives cos ka is equals to 8 pi square m by 2 alpha beta h square times v0 beta b sine alpha a plus cos alpha a. So further it is 4 pi square ma by h square v0b sine alpha a by alpha a plus cos alpha a. So it is simply approximated as p times sine alpha a divided by alpha a plus cos alpha a, where p is assumed as 4 pi square ma divided by h square times v0b. So these equations, p sine alpha a by alpha a plus cos alpha a, this equation is schematically represented in this figure. The quantity on its right side, that is this quantity, is plotted as a function of alpha a. So x-axis is alpha a. The cosine term on the left side, this one, of the equation can only have values -1 to +1. Cos alpha a can take the values from -1 to +1, which is indicated by the horizontal lines in the figure, this one and this one, +1 and -1. A consequence of this limitation is that only certain values of alpha and hence E are allowed. Further, from the left side of this equation, it is clear that for a specific value of the energy, cos Ka can have only one value. Specific values of the energy, cos Ka has the one value only. Moreover, since cos Ka is an even periodic function, it will have the same value whether K is positive, negative, or it is increased by integral multiple of 2 pi. Accordingly, the total energy E of the electron is an even periodic function of K with a period of 2 pi by A. So this is the original figure where we have plotted the energy versus wave vector for a one-dimensional lattice, and this shows a plot of energy as a function of k. If k is to be real, the magnitude of cos k should be less than 1. That is, modulus of cos k is less than 1, which corresponds to the allowed energy band. And on the other hand, those values of energy E for which cos Ka is modulus cos K is greater than 1, only the imaginary values of K are possible, which correspond to the forbidden band. The allowed and the forbidden energy bands are schematically shown in this figure. So from minus pi by 2a to pi by a, this is the first Brillouin zone. The region of pi by a to 2 pi by a and minus pi by a to minus 2 pi by a is the second Brillouin zone. And here U1, E2, these energy levels are discrete, but in between energy U1 and E2, there are allowed and forbidden bands, which are called the energy band gap, as exists in semiconductors and insulators. So further, if we analyze this equation, P sine alpha A by alpha A plus cos alpha A, the left hand side is cos K, right? If we look in this figure, the allowed range of alpha A permits a wave mechanical solution to exist as shown in this figure. Thus, the motion of electron in a periodic lattice is characterized by the bands of allowed energy separated by forbidden regions. These are the forbidden regions, the shaded portions. As the value of alpha A increases, the width of the allowed band also increases while the width of the forbidden band decreases. This is because of the fact that the first term on the right side, that is P sine alpha A by alpha A, on an average decreases with increasing alpha A. And the further understanding, let us look at the influence of P on the energy spectrum. The quantity P is known to be the measure of the potential barrier strength, right? So if P is large, means the potential barrier V0B is large. The function described by the right hand side of the equation crosses +1 and -1 region at a steeper angle as shown in this figure. Thus, the allowed bands are narrower and the forbidden bands are wider, right? This is narrower, this is wider. Hence, the ratio of the width of the forbidden band to that of the allowed band increases. Let us take the case when the potential barrier strength is very large, that is P tends to infinity. However, as the right side of the equation, this has to stay within the limit ±1, right? As the left hand side is cos K, it follows from equation that sine alpha A by alpha A tending to 0, that is sine alpha A tending to 0. That is alpha A is equals to plus minus n pi, and alpha square is equals to n square pi square by a square. So if alpha square is equals to n square pi square by a square, putting the value of alpha square, that is 8 pi square me by h square, e becomes n square h square by 8 m square. So this is equivalent to the case of the discrete energy spectrum of a particle in a constant potential box of atomic dimensions. This is expected because the large p, for large p, tunneling through the barrier becomes almost improbable. That is the case of the particle in a box. So if on the other side P is made to be 0, then this equation tends to cosine alpha is equals to cos k alpha, that is alpha equals to k, that is alpha square is equals to k square is equals to 8 pi square me by h square, and e becomes h square by 8 pi square m times k square. So substituting k is equals to 2 pi by lambda, e becomes this 2 pi by lambda, we have putted it, and h square by twice m times 1 upon lambda square, that is p square by twice m, that is half mv square, where lambda is equals to de Broglie wavelength, that is h upon the momentum p, which is mv, and this is equivalent to the case of the free particle. Hence no energy levels exists allowed, hence no energy level exists allowed. So these are the basic interpretations from the final equation of solution of the Kronig Penney model, that is cosine k is equals to p sine alpha a divided by alpha a plus cosine alpha a. Furthermore, uh, we know that the problem uh, of the motion of the one electron in a three-dimensional periodic potential consider the problem of one electron in a spatially infinite one-dimensional periodic potential by solving Kronig Penney model. Since it is exactly solvable, the Kronig Penney model is very useful for giving some feeling for electronic energy bands, Brillouin zones, and the concept of effective mass. So the potential is mathematically convenient to let the widths become vanishingly narrow, and the uh, height is almost infinity. So except for the definition of the mass, in any equation we can substitute for the small k. We may think that the m star is acting as a mass, and this is called the effective mass. For small k at any rate, we see that the only effect of the periodic potential is to modify the apparent mass of the particle. So the appearance of the allowed energy bands for waves propagating in periodic lattice, as exhibited in the Kronig Penney model, is a general feature. The physical reasons for this phenomena are fairly easy to find as shown in this figure, and consider a quantum mechanical particle moving along with energy E as shown in this figure. Associated with the particle is a wave of de Broglie wavelength lambda, and in regions A to B, C to D, and E to F, etc. The potential energy is non-zero. These regions of hills in the potential cause the wave to be partially reflected and partially transmitted. After several partial reflections and partial transmissions at A to B, C to D, and E to F, etc., it is clear that the situation will be very complex. However, there are two possibilities. The reflections and transmissions may or may not result in destructive interference of the propagating wave. Destructive interference will result in attenuation of the wave. Whether or not we have destructive interference depends clearly on the wavelength of the wave and of course on the spacings of the heels of the potential and hence on the energy of the particle. Hence, we see qualitatively in any rate that for some energies the wave will not propagate because of attenuation. This is what we mean by a disallowed band of energy. For other energies, there will be no net attenuation and the wave will propagate. This is what we mean by an allowed band of energy. The Kronig Penney model calculations were just a way of expressing these qualitative ideas in practice or in precise quantum mechanical form.